Hi guys, this is AP Chemistry, Chapter 11, Section 3. We're going to go over intermolecular forces. Intermolecular forces are the force of attraction between two or more molecules. The state of matter, so solid, liquid, gas, depends on the magnitude of those intermolecular forces among constituent particles relative to the amount of thermal energy. So if you heat them up, then they're going to move faster. They're going to be able to break those intermolecular forces, changing the state of matter with thermal energy. The intermolecular force, the force that holds condensed states together, depends on the size and the polarity of the particle. And that has to do with Coulomb's law. So potential energy is equal to this constant, which we will ignore for a second. The two various charges multiplied together, that would be the proton and the electron in this example, because we have positives and negatives, divided by the distance of separation between them. So potential energy of two oppositely charged particles is going to become less. It's going to decrease or become more negative with an increasing magnitude of charge and a decreasing separation. So what that's saying is, if I were to double the value of Q, so instead of +1 and -1, if it was +2 and -2, I would get a factor of -4. So I would go from a -1 to a -4. The magnitude of that force, or that energy, I should say, is increasing. But when we say low potential energy, usually we start at 0 and it goes down from there. So we're going to be in negative here. So a -4, if the charges were +2 and -2, would be a lower potential energy, technically. Okay, so the greater the charge and the smaller the distance, the lower the potential energy. And low potential energy means stable. So those opposite charges want to be close together. Protons and electrons are attracted because the potential energy is lower as they get closer together. That's what we just went over. Intermolecular forces are generally much less than the bonding forces that are called intramolecular. Why would that be? Why would, for example, in water, the hydrogen and the oxygen be held together much stronger than two water molecules next to each other are held together? It's much harder to rip the hydrogens off of the oxygen than it is to separate two water molecules. Why would that be? If you said the distance between those charges, you are correct. So the hydrogen and oxygen in the water molecule are very, very close together. Their electrons are overlapping. And then if you compare two water molecules, they're going to be much farther apart comparatively. There are 4 types of intermolecular forces. They're listed in order of increasing strength. So the weakest type of intermolecular force is called dispersion force, or London force, or London dispersion force. And we are going to watch a video that shows an analogy of these dispersion forces. So it's really just an interaction of electrons, and we're going to see the interaction of birds that are an analogy for the moving electrons. So all of these are electrons around a nucleus, and you can see that they're moving all kinds of random directions. The more birds there are in a given area, here they're all evenly distributed, but the more birds you get, the more likely you are to get that uneven distribution where all of a sudden part of it becomes darker. So you'll see in a second when it becomes polarized because of some kind of interaction here. So right back there a second ago, there was this high density of birds right here, and then a low density. When we're talking about electrons, since they're moving around very randomly, kind of like these birds are, you get these instantaneous dipoles where for a split second there are more of them in one location than another. and that causes it to be slightly polar, but only for a split second, and then it goes back to being evenly distributed like this. Okay, so the more birds there are, the more chance you have of having that polarized state, and the bigger the cloud compared to down here, the more likely you are to get this, where you have a greater concentration of the birds or the electrons on one side than the other. Okay, so these birds, actually, this is going to be a really good analogy for an induced dipole as well. Why are the birds doing this? It's because there's a larger bird after them. So that larger bird could be, pretend it's another electron of similar charge. It's repelling the other electrons. So if you get two negative ends of the molecule close together, you're going to cause that induced dipole where the negative pushes the other negative away. Okay. And something I want you guys to take away from this video is the more electrons there are, the greater the chance they have of polarizing. Okay, so the more electrons we have, the greater the polarizability. And back over here in the notes. So that instantaneous dipole that we can have is called a dispersion force. So when we instantaneously have more electrons on one side of the molecule than the other, you're going to get a momentary, an instantaneous dipole that then will induce a dipole on the molecule next to it and cause basically a chain reaction. And that interaction between them causes them to be attracted to each other and stick together, even though it's only for a brief moment. So these dispersion forces are present in all molecules. Every single molecule out there is able to have the electrons instantaneously be more on one side than the other. They result from fluctuations in electron distribution within molecules or atoms because electrons at any one instant may be unevenly distributed. So for example, if we had octane, C8H18, this is a nonpolar molecule because it is a hydrocarbon, so the electrons should be evenly distributed throughout the entire thing. I'm just going to draw it as this long oval shape. So those are all the carbons and hydrogens linked together. The electrons should be evenly distributed, but for a brief second, the electrons might randomly be more on this side than the other. Okay, and so for that second, the right side is partially positive, and that's going to cause the electrons to move over towards the left of the one next to it. Okay, and then these are instantaneously going to stick together, and that is why octane is present as a liquid at room temperature. So the reason these molecules stick together and stay in a liquid form at room temperature is because of these dispersion forces. Okay. So that instantaneous dipole just means two opposite sides, on one atom or molecule induces an instantaneous dipole on the neighboring atoms and molecules. The magnitude of dispersion force depends on how easy electrons move around, which depends on the size of the atom, meaning how many electrons there are. And therefore, a larger electron cloud leads to, here's our key term again, you're going to want to write this on the FRQ section, greater polarizability of the molecule, which then leads to larger dispersion forces. Okay, and lastly, dispersion forces can also depend on the shape of the molecule. So if we have a longer chain, like in octane, compared to a little round molecule like methane would be CH4, the small round molecule is going to be less likely to interact with the ones around it because there's less electrons to polarize. Okay, and the long chains are going to have higher melting points. They're going to stick together more. And higher boiling points because there are greater dispersion forces between them. Okay, dipole, these are forces between permanently polar. So polar molecules always have a positive and a negative end. And when you put them next to each other, they're going to attract. So this attraction in between them right here, this is going to be our dipole-dipole force. We have two dipoles. The force in between them that sticks them together, kind of like a little magnet, is called dipole-dipole. I do want you guys to look at figure 11.8 in your book. Look at the relationship between the boiling point that's listed and the dipole moment, which is a measurement, a number describing the polarity of the molecule. And right here, I have some other examples. So for our boiling temperature, you can see that you're increasing dipole moment as you go down, and the boiling point also increases going down. So the greater the dipole moment, the greater the boiling point. Okay, and also I want you to notice they list molar mass for a reason. These molar masses are also going to affect, because we said there's two factors. There's the polarity, which is described by this dipole moment. This is the polarity. And also by the size, also the mass. So we haven't talked about which one affects it more, and it really depends on the molecule. Okay, so for this one, these are all very close to the same mass. We're not comparing one of like 10 atomic mass units to one of like 100 atomic mass units. These are very similar in size. So the dipole moment is what's really affecting boiling point. A permanent dipole just means there's a permanent partial positive and a permanent partial negative charge on the molecule. So like we had up here with HCl. Okay, let's look at this other example. I have CH3, that's a methyl group, with chlorine, CH3 with bromine, and CH3 with iodine. Okay, so these are, the polarity is listed here, the dipole moment of each. They're close, okay, they're similar, they're all polar. They all have a dipole moment greater than 0, so they all have some kind of polarity. And their polarity is similar. So looking at the boiling point, this one is contradictory to what we just said. This is a very low boiling point for CH3Cl, given that it has the greatest dipole moment. So what is really going on here? What's going on is the one with the greatest boiling point had the lowest dipole moment, has the least polarity, but it has the smallest difference in electronegativity of the atoms in there, but it's because of its size. So there are way more electrons in iodine than there are in chlorine. Let's look over here. Iodine has 53 electrons and chlorine only has 17. So the greater number of electrons is leading to greater polarizability, which leads to a greater boiling point. Okay, a few things to remember. All molecules, every single one. So if it asks you to list the intermolecular forces, you automatically put dispersion forces. Polar molecules have dipole-dipole forces in addition to. So if you're talking about HCl, you're going to say it has dipole-dipole forces, and you're also going to say it has dispersion forces. The additional attractive force raises their melting and boiling point. So for the polar things, they're going to have higher melting and boiling points. Miscibility is a definition in this section that we need to know. Miscibility, I like to call it mixability. It's the ability of two liquids to mix without separating. So, for example, rubbing alcohol and water are miscible. You can mix them together in any amounts. Oil and water are immiscible. They do not mix in any amount. Hydrogen bonding is a type of dipole-dipole. So it's where polar molecules containing hydrogen directly bonded to a small electronegative element, F, O, or N. Okay, fluorine, oxygen, and nitrogen are the key. They have to be bonded to hydrogen, and if they are, then they're going to exhibit a stronger than usual intermolecular force called hydrogen bonding. It's like a super dipole-dipole force, so it's a type of dipole-dipole. Okay, so if I am asked to list all of the intermolecular forces in H2O, Water is polar, so it's going to have dipole-dipole. It has dispersion forces, because they all do. And hydrogen is bonded to oxygen, so water also has hydrogen bonding, as does NH3, where the H is bonded to nitrogen. Okay, so this is ammonia. Ammonia also has dispersion forces, dipole-dipole forces, and hydrogen bonding. Okay, and last but not least, we have ion dipole forces, which are the strongest because unlike these ones up here that had a partial charge because they're covalent, now we have an ion involved, and an ion is completely charged. So it has gained or lost an electron, and we're combining that with a little magnetic, a little polar molecule. Okay, and when we combine the two, a really common example is sodium chloride in water. You're going to have the water separate the ions from the solid, from the crystal lattice here. And notice that all of the negative parts of the water, the oxygens, are all pointed towards that little sodium ion. And then if you look down here at chlorine, you have the positive hydrogens pointed towards that chloride ion because their opposite charge is attracting. Okay, this is called hydration when you surround the ions with water. All right, for a summary, I would like you guys to list the 4 types of intermolecular forces and kind of what they are so that you know what they are. You can look at the conceptual connection 11.4 on page 498. You do not need to write the answer to that conceptual connection down. I just want you to quiz yourself. And then I do want you to look at DNA on page 499 as well. You do not have this as homework. You're going to have your practice problems. That's supposed to be an X. And I did want to note that, look at this. We are so close to being right on track, even with all the craziness that this year has thrown at us. So you guys are doing amazing, and I will see you all tomorrow. Have a great day.